Now let's focus on organic molecules or charged species in organic chemistry. And we'll look at the stability of each of those, and this will be very important for the reactivity that we'll see later on in other studies. So let's look at the stability of an alkoxide. So we have ethoxide here, and this is kind of a neutral situation, and we'll compare that with a chlorine added onto the chain. Now, when we add an electronegative atom onto the chain, this will have the effect of pulling electron density away from this charge. That will stabilize this negative charge. So, since it's electron withdrawing, because it's electronegative, this will help stabilize the negative charge. Now, we could compare that with a positive charge, and it should have the exact opposite effect. And it does. This chlorine will destabilize the positive charge. So this species would be harder to form versus the one that doesn't have the electronegative atom on it. Conversely, it would be a little bit easier to deprotonate the neutral species with the electronegative atom added. So this should have a lower pKa than this molecule than ethanol. So let's see here. That would be 2-chloroethanol would have a lower pK than just ethanol. Let's look at some electron donating groups. And one of the ones that we'll see a lot of is just like a CH3. So this has a little bit of electron donating capacity. So we're sending electron density into this carbon. Now let's compare that with, should have left myself some more room here. With something that has several electron donating groups. So these are all sending electron density into that carbon. Now it already has plenty of electron density right here in the form of a negative charge. So it doesn't really need additional electrons because it's got a lot of them right here. So this particular species will be less stable. than the comparative with less electron donating groups. Here we only have one. Hydrogens don't really do much electron donating. So what does that mean? That means that this is a better base than, so the T-butoxide is a better base than the ethoxide. And you'll see that later when we start talking about elimination reactions. We'll be using this base in some of those cases. So that makes, again, this negative charge less stable. So it's more likely for it to want to pick up a proton. It's harder to remove the proton because this resulting anion is less stable. Those are the ways that we can look at this. Now, let's look at carbocations. So we're going to use this extensively in organic chemistry. So we have a methyl carbocation, and then we could have a primary carbocation, which has some carbon group, some CH3 or CH2, CH3, or whatever we want. But let's just stick with hydrocarbons here. This is a primary. We could have a secondary, which has 2 carbon groups on it. And then finally, we can have a tertiary carbocation. And that's as high as it would go. I've listed these in order of their stability. So methyl groups are the least stable. They have the least electron donating. So here we have a carbon that's electron deficient. So it wants to have electrons sent into it. Up here we had an oxygen and a carbon that had excessive amounts of electron because it's negatively charged. Down here we have the opposite of that. So now we want electron donating to happen. So a primary is significantly more stable than a methyl carbocation. A secondary is a lot more stable than the primary. And the tertiary is the most stable out of the carbocations. This is the easiest to form. So let's review some of this. We have electronegativity, which will be an electron withdrawing group. The higher the electronegativity, the more electron withdrawing it would be. So if instead of, say, a chlorine, we had a fluorine here, that would be even more electron withdrawing, and it would stabilize this negative charge even more. Or, conversely, it would destabilize this positive charge even more. If we have electropositive groups, like electron donating, then that will stabilize positively charged things. And something like a silicon group, like a silyl group, is even more electron donating than the equivalent carbon group. So this will have an even greater effect than an R group would, like with just carbon on here. if you have a charged species, that will have an enhanced effect. What I mean by that is if there is a positively charged species somewhere on the molecule, that will steal electrons even more than a fluorine would, because now it's electron deficient in enough of a way that it's positively charged. So each of these is way more electron withdrawing or like desiring electrons than even fluorine is. Conversely, if we had a negative charge on something, that's even more electron donating than silyls or other groups that are very electron donating. If we add more groups to something, we will have a greater effect. You can see that between the methyls and the primary, secondary, and tertiary. But you can also look at that in terms of these. Like if we were to add more chlorines on here, it would have a greater stabilizing effect because there would be more electron withdrawing, and that would stabilize the charge. And then the distance that we have, each of these groups makes a very large effect. If we were to have a longer chain and the chlorine was located further away from the negative charge, it will have less and less of an effect than if it is located closer. And if instead of having this on the second carbon away from this, we had it on the first one, that would have a greater effect. And we saw this when we were comparing the various butanoic acids, where we moved the chlorine closer and closer to the carboxylic acid group. And as we got closer, the carboxylic acid got more acidic. That's because we were moving the electron withdrawing atom closer to where the negative charge would end up. That has a greater stabilizing effect by having it within proximity. So, with that, that is a discussion on organic charge stability. Thank you for joining, and we'll see you in the next video.